So here we go with intermolecular forces, intermolecular, international, between nations, between molecules. So as a review, we know that molecules are far apart, random, fast moving motion. They fill up the shape of their container, so they have an indefinite shape and an indefinite volume. They still do have mass and occupy space. And they have the lowest intermolecular forces when comparing same species, because a cube of ice has a very, very nice structure. This is definite volume, definite shape. So this is going to have higher intermolecular forces, forces holding the molecules together than a gas with all those random ones. Now, the kinetic molecular theory, of course, does not follow all this, and it has slightly different rules. But for this standard, we're focusing on what a gas actually does. Okay, so when you have a gas leaking out of a container, that's called effusion. And when it's spreading out, like in a room, that's called diffusion, like a diffuser you might have seen someone have where it spreads out the smell. Okay, and so both methods of those are comparing the speeds of the gas molecule. If you are a lighter gas molecule, zoop, you can zip right over. If you're heavier, it takes you a little bit longer to get started. So how do you know which one's going to be travel faster? Compare the molar mass. Lower molar mass, it's going to travel faster. Okay, higher molar mass, it's going to travel slower. Again, nice little visual here. Typically, you are going to see those intermolecular forces, between molecules. You're going to see them as dashes or as dots, not as solid bonds. Why? Because they're not bonds. They are forces holding the molecules together. Where the intra are the inside forces. In this case, between the carbon and the hydrogen, that would be a covalent bond. These inside forces are a lot stronger. It is easier for me to break apart molecules than to break apart one molecule. So when we have to determine IMF, if there is only two atoms, you're going to just find the bond polarity by subtracting their electronegativities. Otherwise, you're going to draw their Lewis dot structure and decide if they're polar or nonpolar. This is for covalent. If you're ionic, you are going to have the strongest intra bonds. So you're going to be at the top of the chart for year one, and then covalent would be the next strongest intra-bonds. And then we go to the IMFs after that. And those would be the IMFs for the covalent bond. So you're still doing the same thing when you're finding the name in the formula. See if they're ionic or covalent first. Ionic for year one are the strongest. And then we got to rank the covalent based on their intermolecular forces, their forces between the molecules. Okay. And polarity is the way to do that. And there's just a quick review about how to find the Lewis dot structure. You can also watch a video on finding that Lewis dot structure. So here is the main table that you have that relates all of these items. The intramolecular force, notice we're just doing covalence there. Ionics are at the top. Hydrogen bonding is the strongest of the intermolecular forces. That's why it's at the top. And then dipole's next, and London dispersion is at the bottom. Okay, so the strength of the IMF is listed here on the table. The ones not labeled, those are just in the middle. Strength is opposite the vapor pressure. Strength is direct with the boiling point. So if you have a strong strength, you have a low vapor pressure and a high boiling point. That makes sense because a low vapor pressure means it doesn't have a lot of peer pressure to turn into a gas. If you have a high boiling point, it takes a while to turn into a gas. So it's the same thing, just worded a little bit differently. Number one thing people mess up here is hydrogen bonding is only if you see inside bonds of HF, HO, and HN. That's the only time you see it. So you can have hydrogen and fluorine in a molecule and not have hydrogen bonding. This table would be important to memorize. Okay. These things, the intermolecular forces, affect your physical properties. It affects the vapor pressure, the ability to turn into a gas. It affects the boiling point, the ability to turn into a gas. It also affects things like solubility and surface tension. Okay. This is going to be a table that you're going to use as an absolute for year one, but later on, you're going to learn that you could have a particle that is so massive that it's actually stronger than the hydrogen bonding because it has pulled together so much mass, just like a large planet or a star has pulled together a lot of mass, and it can pull you in there with those forces. So vapor pressure, again, the ability of a substance to change into a gas, and it's the pressure that you measure above a liquid in a closed container. Higher vapor pressure, more pure pressure, easier to phase change. So your boiling point is lower. When the atmospheric pressure equals the vapor pressure, then that liquid is out of there. It has met its limits. Okay. How about solubility? Okay. Like dissolves like. So polar substances dissolve polar. That's why water is the universal solvent. It can dissolve polar substances and ionics. Okay. Non-polar substance dissolve non-polars. But we got an added layer here. When we're talking about temperature, for solids, as the temperature increases, your solubility increases. If you have sugar in iced tea and sugar in hot tea, you're going to get more sugar able to be dissolved in that hot tea because it's warmer. But gases are the opposite. If I have a cold soda, it doesn't taste flat as fast as a warm soda because we have more carbon dioxide that is able to go into solution when it's cold. So gases are the opposite typically of solids when we're talking about solubility. A volatile liquid is just one that changes to a gas rapidly. A non-volatile liquid changes to a gas slowly. Volatile liquids have vapor pressure. All right, so let's try one of these higher level questions. Separating carbon dioxide. So right now we were just talking about carbon dioxide, carbonated beverages, that's a gas, from a solution of carbonated water. Okay, so we're still using water as our liquid that is the universal solvent. How can we most rapidly or most quickly separate it? So what do we need to do? We need to decrease the solubility. We got to make it warmer to decrease the solubility. We got to make it go flat. We got to get those carbon dioxide bubbles out of there. Okay, so how do we make it go flat? Increasing the temperature. So C and D have that. We're going to cancel off A and B. Increasing the temperature will increase the ability for it to leave solution. Okay, what about the pressure? What about the pressure? Okay. If we increase the pressure above the surface, then that's going to be more pressure pushing down on it. What's going to happen? Again, it's going to stay in a liquid state. It doesn't want to deal with that extra pressure. So our answer is D. All right, so now let's make sure we can measure our IMFs. Water is H2O, dihydrogen monoxide. Oxygen goes in the center, hydrogen the outside. Hydrogen can only single bond. Now I check my valence. Oxygen has 2 valence electrons shown, but he's supposed to have 6. So I'm going to add 4 more. 6 valence electrons plus 2 more is my octet. So that is how that structure is going to look. So I can now draw it with just those single bonds there. Okay. My shape, 2 outer atoms, hydrogen and hydrogen, and 2 lone pairs, unbonded electrons on the center atom. When I look on my table, that is a bent structure. Polar or non-polar? If you see 1 to 2 lone pairs, unbonded electrons on the center, it is polar. So this guy is polar. Does it have dispersion forces? This is the weakest one. Okay, but we start with that one. Why? Because all molecules have dispersion forces. You see a covalent molecule, you're going to write dispersion down. Dipole, dipole, pole. That happens when it's Polar, that's its name. It has two poles, a positive and a negative pole, not as strong as an ionic, but it has two poles, dipole, dipole. This guy has those negatives there, and then we'd have the positives. So we have poles going on. So this guy is polar. Hydrogen bonding. That only happens if we have intrabonds of HF, HO, HN. We have to see the fun, okay? So one of those actually with a single bond to the hydrogen. Right here, we have one HO, two HO. So we actually have two spots of hydrogen bonding. So hydrogen bonding gets a yes. Okay. Has to be intrabonds. Okay. Vapor pressure estimate. We have the strongest IMF. Okay. And IMFs and vapor pressures are opposite. So we have a low vapor pressure. It has a low pressure, pure pressure to turn into a gas. Water is the liquid at room temperature. So that makes sense because it takes a while before we get up to 100 degrees. So it has a low vapor pressure, and then it would have a high boiling point. What next? Carbon tetrahydride, CH4. Carbon goes in the center. Hydrogen does single bonds around the outside. This has 4 outer atoms. So this is a tetrahedral shape. Tetra means 4. Polar or non-polar. We have all the same outer atoms, so that's not messing up our symmetry, and we have no lone pairs. So that means this guy is non-polar. He has totally an equal distribution of charge. There's no super strong pole of negativity pulling off somewhere. Dispersion forces, does it have? Yep, all molecules have dispersion. Dipole, dipole. It's not polar, so it has no dipole, dipole, has no poles. Okay, it actually has instantaneous poles, but it has no permanent poles. Hydrogen bonding, nope. I have hydrogen, but hydrogen here is bonded to carbon. So can't be hydrogen bonding because an HC is not part of FON. It's not fun. Vapor pressure. This guy is non-polar. It has only the weakest of the IMFs. Vapor pressure and IMF are opposite. So it has a low strength. So it succumbs to peer pressure easily. So high peer pressure, high vapor pressure. It succumbs and becomes a gas quickly because it's not very strong, a low boiling point. Vapor pressure and boiling point are opposites. Methane, which is carbon tetrahydride, is a gas at room temperature. So low boiling point confirms it's probably a non-polar substance. It needs less energy to break apart those intermolecular forces. We're not talking about intrabonds. We're not talking about the covalent bonds on the inside. A CH bond is hard to break. A HO bond is hard to break. We're talking about the ones that are weaker, the intermolecular forces between molecule forces. Draw carbon trihydride monofluoride. Carbon with 3 hydrogens and 1 fluorine. That fluorine there, let me draw it somewhere else actually, so you can see it. That fluorine is not going to stay like this. Fluorine has 7 valence electrons, so we got to show that on here. Okay. Those 7 valence electrons are giving it a very, very negative pole. So this guy is polar, even though he's still tetrahedral. It's still 4 outer atoms, but they are 4 different outer atoms. So they are pulling at different abilities because they have a different distribution of electrons. Electrons are what's helping it bond, those negative little bits. It is polar, no lone pairs, but it's not symmetric. Okay. All molecules have dispersion. All polar molecules have dipole-dipole. Does it have hydrogen bonding? That is only when you see HF, HO, HN on the intra side. I have CH, 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 and CF. There is no hydrogen bonding here. Even though there's hydrogen and fluorine there, they are not bonded together, so they do not count. Okay, so this guy is basically in the middle. It has basically a medium amount of IMF. It's not as strong as hydrogen bonding, but it's stronger than dispersion. So when you're ranking these, you got to make sure you're comparing apples to apples. This guy would be weaker than the water, but it would be stronger than the methane, which was all nonpolar. So it's typically going to have a higher vapor pressure than things with hydrogen bonds. It's typically going to have a lower boiling point than hydrogen bond ones. So always use that table we started with to work on ranking. Fluorine gas, F2, don't just cause one F. Why? Brinkelhoffs, there's 2 fluorines. Its shape is linear. I don't even have to draw this guy, right? Because 2 points is always a line. It's always 180 degrees apart. Okay, there are no lone pairs because there's no central atom. The change in electronegativity, 4 minus 4, 0, nonpolar. All molecules have dispersion, but he's nonpolar, so he has no dipole-dipole. He has no hydrogens, so even though he has fluorines, there's no hydrogens. Okay, what's his vapor pressure? He is nonpolar. He only has the weakest IMF, which means he's going to have the strongest vapor pressure. He is going to quickly and rapidly give into that pure pressure to change to a gas, which means his boiling point is going to be low. So if you can identify each one, then the next step is making sure that you can compare to. Which of these has the lower vapor pressure, carbon tetrafluoride or carbon tetrahydride? Draw both out. These guys are both nonpolar. Why? They're symmetric. We all have the same outer atom of fluorine, even though this one's not completely correct drawing. It should have all those valence electrons there. So it has a high electronegativity difference, but it's all going to cancel out because it's symmetric. So no lone pairs and symmetric, nonpolar. Carbon tetrahydride, nonpolar. So none of these have the hydrogen bonding. None of these have dipole-dipole. So when we're ranking these guys, we only have London dispersion. All molecules have London dispersion, but you have more dispersion if you have more mass. Carbon tetrafluoride has more mass. It has a higher molar mass. Okay, so when we're looking at here on just this bottom row, carbon tetrafluoride is going to be higher than carbon tetrahydride. So carbon tetrafluoride is going to have stronger IMF because he's higher up on the chart. Carbon tetrafluoride and carbon trihydride, this time we're going from high to low. So carbon tetrafluoride is going to have a lower vapor pressure. What about if we're comparing boiling point? Carbon tetrafluoride has more mass than carbon tetrahydride. We're going from low to high, so it would have a higher boiling point. Hey, that makes sense. It has more mass. It would take longer for that mass to boil. Makes sense. You can go back and use your knowledge that way. So even if you have ones that are all nonpolar and you can't rank them based on the other things, it still fills in the chart for ranking and comparison purposes. Okay, this guy, I don't know what the molecule is, so I can't find the molar mass. I can't draw the molecule. The only thing they gave me is boiling points. What do I know about boiling points and IMF? Okay, if I have a high boiling point, I have higher intermolecular forces. What is the highest boiling point here? That's this guy, because these are negatives. So the smaller number is going to be closer to the 0 and to the right side. So the highest IMF is going to be C. The lowest IMF is going to be B. Higher boiling point, higher intermolecular forces. You could also figure out vapor pressure. Vapor pressure and boiling point are opposites. What if it's an ionic bond? Let's review right what I said at the beginning. For year 1, ionic bond's going to be the strongest, and then hydrogen bonding, and then dipole-dipole, and then dispersion. just for year one. Okay. An ion dipole is what an acid has. Why? Because an acid, H2SO4, sulfuric acid, this side is covalent. Okay. And this side, when they combine the H and the S4, that has ionic tendencies. Even though hydrogen tends not to be ionic, when it's in solution, it does make ions. So this one is ion and dipole, a polar and ionic situation. So still pretty strong. Okay. And lastly, just a reminder, it takes energy to break bonds. Okay, because I want to break them apart. I got to be strong. I got to take that energy inside the bond, endothermic. Okay, so if I'm making a bond, I'm releasing energy. I get endorphins. I'm now going out with somebody. Woohoo, I'm happy. I'm releasing some good energy to the world. So that's what you need to remember for those bonds. And that's all for today.